What's up, high elves, goblins, and children of the fifth age? What's poppin'? Today, we're gonna talk about torque and angular acceleration, which is gonna be so tight. This is how you're gonna not snap bolts in your car. So this has some real practical applications that you're gonna need to know about for literally the rest of your life. I can't get up out of bed without torquing my knee out of or without using this in a productive manner. So, yeah, let's talk about it. It's gonna be tight. You're gonna like it. And it's not too bad. From here on out, I feel like we're in the home stretch, and we got the easy road ahead of us because you already know everything about physics. Now you just have to do it again, but while spinning. So it shouldn't be that bad. So let's take a look at torque and angular acceleration and learn some stuff we already know. So to open your mind to the idea of torque, let's talk about the best way and the worst way to open a door. Okay. Let's talk about the best way first, right? Because I feel like this is maybe more intuitive than bad ways. You guys are really great at opening doors. I've seen you guys open so many doors. I'll close my classroom door, and then without even asking, you'll open it, and then you'll walk in. Well, not you guys, because you guys are online, but people do this to me, and it's how rude, right? They don't even knock. But so if we've got a door, let's look at our door like this, and you got a little doorknob there. And then you walk up to this door. You got a little longer legs than that. You like dance towards the door, and you got really long spider limbs. So you're gonna walk up to the door. You're gonna grab the handle, and you're gonna push it that way, or maybe pull it. Either way will work, all right? But you're gonna grab the handle and push or pull. So the best way to open the door is maybe grab the handle and push or pull. Hopefully you can read like the little sign on it, right? And it says like pull or push. Because if you try and push a pull door, you're out of luck. That's not going to work at all. But if you try and pull a push door, that won't work either. So you gotta know your limits of your door. Okay. Now here is the interesting way. Let's talk about wonderful ways that we could not open a door, right? You have to try and open the door, but not open the door. Some students really struggle with bad ways to open the door. So let's talk about them. Let's say you've got a door here, and you've got your hinges right there, right there. Let's say you walk up to the door, and instead of grabbing the handle, oh, I erased your whole body. You push on where the hinges are. You push right there. Is that door going to open? Absolutely not. There's no way this door is opening. If you push on the hinges, you idiot. How dare you try and open a door like that? That's not going to work. That's dumb. That's a terrible way to open a door. Okay. Let's think of other creative ways to not open a door, shall we? What if you've got a door, a little crooked, hinges. What if you get on this side of the door and you push on the edge of it like that? If you push this way on the door, and I mean like straight into the door, no like out of the door or like behind the door stuff. I mean, you push straight on the like, let's make it 3D, on the edge of the door, and you push straight that way into it. That door's not going anywhere unless you're pushing unbalanced, right? But if you push on that door, that thing is staying closed for so long. So here are some good ways to not open doors, right? What's another way we could not open a door? You probably couldn't like try and lift it like that. If you try and open the door by trying to like lift it this way, that's probably not going to work. That's not going to happen. I'm sure there's other ones. Be creative. You can come up with some pretty darn ways to not open a door. Pretty darn bad ways to not open a door. So, what did we learn from this? Let's talk about it. So, the reason there are bad ways to open doors is because to open a door, you have to apply some torque to the door. Because typically, when you approach a door, it's at rest. It's just sitting there minding its own business. You have to accelerate the door to get it to move, take it from rest to moving. There's an acceleration there. Typically angular. You want it to spin around the hinges. So we have to apply a torque to give it an angular acceleration such that the door will open. So let's talk about the two different expressions we have for torque. The first of all, this and this, these are tau, and this is the Greek letter for torque. So torque is equal to the moment of inertia. Remember, this is spinny mass times acceleration, times angular acceleration, to be specific. So torque equals spinny mass times spinny acceleration. Force equals linear mass times linear acceleration. Torque is force, but for spinning things. It's the spinning force. So if we apply a torque to something, it will angularly accelerate. And this is kind of like Newton's second law, but for spinning things. Beautiful. Okay, so that one we could probably guess. That's just Newton's second law. This is the one that is rotational specific. This is not, this doesn't really have anything to do with, what's the phrase? Linear forces. There's not like a linear equivalent to this. But I did just think of something that is pretty close to. So let's talk about this version of torque. This version of torque says that the force being applied, times the distance from the axis of rotation times sine theta. Theta is the angle between R and F. Okay. And I'll show you how to draw those two things in a second. But this is saying I have to push on something a little ways away from the axis of rotation. And sine, if we will recall from our math class, sine starts at 0 and looks, oh, that's so ugly. I should be ashamed. Let me try that one more time. That's a little bit better. Starts at 0. This maximum at 1 happens at 90 degrees. We're not going to really worry about this half of it because that half is you're just on the other side of the door. So really you just care about from 0 to 180. Okay. So we have a maximum when we are perpendicular and it drops off symmetrically on both sides. You're at 0 when you are at 0 degrees or 180 degrees, meaning you are like in line with R. So you got to push against something, you got to push into it. You can't push parallel to the surface. So let's bring this back to our idea of doors. So we said the good way to open a door Let's try one more time, Mr. Barton. Did you guys just hear that? He sneezed. Okay, here's our door. If we apply our force on the door handle and we push that way on the door, our axis of rotation is going to be wherever the hinges are because it's rotating about this invisible axis where the hinges attach the door to the wall. We're pushing that distance r from the axis of rotation, and our force, this makes a right angle here. So this sine is 90 degrees. So 1, when sine is 90, this is just 1, so it kind of goes away. So it opens, right? Let's talk about the bad ways to open a door. Okay, if we look at this bad way, if you push on here, on the axis of rotation, then tau equals F times R is 0 sine of theta. So it doesn't matter how hard you push or what angle you push at. Because you're on the axis of rotation, your torque is 0. If you push on the thing you're trying to spin around, it won't spin. That kind of makes sense. You can't push on a door hinges and expect a door to spin. Okay. Likewise, if we look at this guy here, or girl, it could be a girl. Not that girls have to have long hair, but you know. The problem here is our torque. We're pushing at a distance r with some force F, but our force is this way, and our R is from the axis of rotation to where we're pushing at. These are parallel, but facing the opposite direction. So that would be 180 degrees to each other. So sine of 180 is 0. Because you're pushing towards the axis of rotation again, even though you're farther away from it, the angle is 0. So 0 times anything is 0, and you apply no torque again. Sneaky, huh? So that's another bad way. The problem here is not so much that we're not applying a force perpendicularly at a distance from the axis of rotation. The issue is these things are bolted to the door. So there's something else trying to counteract that. So that brings us to maybe the next thing we need to talk about torque. Maybe not. Maybe we'll get there. We'll get there in this tug of war. But so really you have 3 ways that you can manipulate torque. You have 3 variables that you have some sort of control over when you're trying to apply a torque to something. You can change how hard you're going to press on something or pull on something or twist on something. The force that you apply can be changed. You can push harder, you can pull harder. Likewise, if you're trying to twist something, you could give yourself more leverage by getting farther from the thing you're trying to twist. This is the idea behind getting a bigger wrench. Let's say you've got like a bolt, right? And then you put your, I got to draw this bolt, and you put your wrench on it. So you got, what do wrenches look like? Something like that, right? And then if you pull near the bolt, if you are right here and you pull that way, you're not going to be able to pull super hard. Sometimes people do this to just barely get it loose. But if you have to really pry this bolt out of whatever it's in, you grab the end with both hands and you crank the heck out of that thing. But you grab the end of the wrench. You don't grab as close to the bolt as possible because you don't have enough leverage on it, right? It's the same reason that you don't, like, it's really hard to just take, like, your fingers, right? What do oh, geez, we're in danger now. Ooh, looking good so far. Like that. Yeah, you're Mr. Krabs now. You couldn't use your fingers to try and twist a bolt, right? It's because your axis of rotation is whatever that is. It's the width of the bolt. By putting this arm on it, you're extending your lever arm and you can apply more torque. You can multiply your torque just by moving farther away from it. There are things that mechanics have called breaker bars. And basically what it is it's a wrench. So let's put our wrench back on there. Right? It's a wrench, but then it's got like another bar that just sticks on the end of it, and then you pull way over here. You, when in doubt, just get a longer wrench. And then the other options we have are changing the angle at which we're pushing, right? If I pull straight perpendicular, this is R from our axis of rotation to where the force is applied. That's R. This is F. This angle here is theta. If we make theta 90 degrees, that's a maximum because sine of 90 is 1. And then if you increase or decrease the angle, it starts to go down. On our sine graph, here's 90. If you go increase towards 180, the value of sine goes down. If you go back towards 0, the value of sine goes down. So you can change your angle. Perpendicular is best. You can get farther away from what you're trying to spin. Farther is more torque. Or you could just straight up pull harder. Okay, cool. So there's the 3 ways that we can goof with torque. Let's go look at some torque problems and dabble with them and make sure we understand what we're talking about here. Let's talk about torquing bolts first. We'll return to the tug of war. That one's maybe a later concept that I want to reorder here. So a student is working on her car and needs to torque a bolt to 50 foot-pounds, but this student isn't fortunate enough to own a torque wrench. I know. So torque wrenches have a torque measuring device built into them. And when you pull with enough torque, they click. And they're like, hey, that's enough. Quit pulling. If you pull harder, you're going to snap this bolt off. And then your dad's going to yell at you and tell you that you're never going to be a good mechanic and make you want to change career paths. But I'm just, I'm minding my own business. So luckily, the student has a small carpentry business on the side and has a digital scale to weigh packages for shipping. So when I say a digital scale, I'm thinking something like this. And it's got like a little handle. So you hang it on here. And then you hold this and it's like 30 pounds. That's what I'm talking about. So digital scale is something like this. It's got a hook on it, maybe like a little handle to pull on or something. The student hooks the scale under the end of their 8-inch wrench, regular wrench, and pulls. Not a torque wrench, a regular wrench. What force should the scale read for the bolt to be torqued correctly? Okay, so here's our bolt. Here's our wrench. Something like that, right? I don't know. Okay. So something like that. There's our stuff. This is 8 inches long. So we'll say from the center to the end where we hook our force gauge onto. This radius here is 8 inches. And I'm as appalled as you are. Inches, Mr. Barton. Ugh, disgusting. You're going to make me vomit in my mouth. I know, me too, kid. But unfortunately, Bolts and wrenches and torques and stuff, as far as cars are concerned, are typically the imperial units, the more disgusting of the unit. Okay. And our force, we're going to grab this thing, we're going to pull on it. So our force, we'll just say it's perpendicular for the sake of making our lives a little bit easier. We want to know what is the force here that we need to pull with in order to get the proper torque. Because if you pull too hard, you can snap these off, and then you have a bolt stuck in your motor. And if you thought torquing something with a thing built to be torqued is difficult, imagine cutting that thing off. It's so much harder to remove. So we want 50 foot-pounds. So our torque equals 50 foot-pounds. Okay. This 50 equals force times R times sine theta. So instead of newtons, we're using pounds, and instead of meters, we're using feet. Normally, the units we will look at are Newton meters. Don't ask me why these are in foot-pounds. I don't know why they switched the force and the length. Americans, I'm telling you. Normally, torque is measured in Newton meters, and that's newtons times meters, and you just say it Newton meters. But we want to be 50 foot-pounds. Okay. So our force times our length has to be 50. Okay. Because we're pulling perpendicular, theta is 90. So this is 1, and it just goes away. So we need 50 to equal our force times our radius. This is in feet. This is in inches. So let's go ahead and convert our 8 inches into feet. So we have inches times, we want the inches to cancel. So we'll put on the bottom, we'll put the feet on top because that's what we want to end up with. There are 12 inches in 1 foot. So we have 8 over 12, which is 2 over 3. So 2 over 3 feet, 2/3 of a foot. So R is 2/3, and we just need to find force. So plug in 2/3 here. 2/3 times F equals 50. To divide by a fraction, we multiply by the reciprocal. These cancel. 3 times 50 is 150. Divided by 2 is 75. So our force has to be 75, and our force in this case is in pounds. So you have to put 75 pounds of force on your wrench. So probably if you are good size weight, you could just grab onto this thing and like lean back. That would probably work fine. But be careful not to go over 75, because if you apply too much torque to this, like 80 or 90 or 100, then this thing can just snap off, and then you're left with like this, and it's just a flat bolt with the threads in there, and it's just in there for the rest of your life. You gotta throw the whole car out. Not really. There are ways to get it out, but it's a lot harder than just using a torque wrench. So the moral of today's lesson is just use a torque wrench. Okay, let's go back to our tug of war problem. This one is more than just goofing about with your torques and calculating a torque. Okay, this one has to do with the same way we have balanced forces, we can balance torques. So let's read the problem. In the Science Museum, there's a large lever with 2 ropes attached, one about halfway up the wall and the other near the top of the wall. The wall? I don't know why I put wall. This should say lever. I think I meant a wall, because in my head it's kind of a wall, but it's a lever. Let's be consistent. So there's a large lever, and about halfway up the lever, there's a rope about, let me just draw you the picture, to be honest. All right, here we go. Here's what you have. You have a lever. Near the top of the lever, there's a rope tied to it, and then there's going to be a kid pulling on the rope. On the other side, wrapped around the middle of the lever, there's another rope, and then there's a slightly bigger kid who's pulling on this one. And they're going to play tug of war with this apparatus here. So, that takes us to here. A boy stands on the side of the lever and pulls the rope attached to the middle lever with a force of 100 newtons. So the tension here is 100 newtons. His rope makes an angle of 90 degrees with a lever. So this rope is at a right angle. He's pulling straight away from the lever. The boy's younger brother pulls on the other rope, but because the rope is a little higher up and this kid's kind of short, this angle here is going to be 60 degrees with the board or with the lever. How hard does the younger brother need to pull to win the tug of war? So we want to find T2. Okay. Do I tell you the length of the lever? The entire lever is about 2 meters. One of the ropes is halfway. So this first one, this distance is 1 meter. And then this distance is 2 meters. Okay. So this kid is 2 meters away. This kid is 1 meter away. Okay. So we want to know, how hard does this kid need to pull this pivoting lever that way so that they win? And I believe in the actual thing, there's like a bell here or something to that effect. And then there's a bell here. And the first person to ring the bell wins. So you got to get the lever to hit the bell. That's how you know you finished. So how do we set up this problem? How do we go about this? So if we recall linear stuff, if I have, let's say, a box, and someone's pulling this way with a tension, and someone's pulling this way with a tension, what we would do is we would write a sum of forces equation in the x direction. We would say T1 minus T2. If we want it to accelerate this way towards the younger kid, we would say equals MA. Okay. What we really want, though, is we want to know, how hard does this kid need to pull to balance this, to exactly split even? And then we just say bigger than that number, and then we've got it. So what we're going to do is we're going to say is 0. We'll find the balance. We'll find the value for this that makes it cancel out, and then we'll just say more than that. Okay. Let's try and apply this same strategy to this. And you're going to say, Barton, can I do that? To which I'm going to say, absolutely, you can. So just like linear forces, we can do a sum of torques equation. What we need to pick, though, is we need to pick which way rotating do you want to be positive. Convention says that counterclockwise is the positive rotation and then clockwise is the negative because we're right-handed. So let's say that this way is positive. So we have positive torque 2. So this is the torque because of the tension in this rope, minus the torque from the tension in this rope, torque 1, equals 0. Normally what this could equal instead of 0 is from this other definition that we talked about right here. If it's not 0, it's going to equal I alpha. But we want them to balance. So in this case, alpha will be 0, and this whole thing is 0. Okay, so now that we have our sum of torques equation set up, we can substitute these torques for the torque equals force times distance sine theta, and then we can do the calculation from there. So Let's go ahead and do that. Torque 2 is going to be the force applied by the rope, so tension 2, times the distance from the axis of rotation. We're rotating about this axle pivot thing here, and we said that's 2 meters away, so times 2. And then the angle that this rope makes with the lever is 60 degrees. So this will be sine of 60 degrees. Okay. Then for torque 1, we're going to have minus the force of tension 1, which is 100, times the distance, which is 1 meter, times sine of 90, which is 1, equals 0. Okay, so we're almost there now. So T2 times 2, sine of 60 is, let me just double check. I believe it's radical 3 over 2, but we'll double check real quick. It is radical 3 over 2. So as a decimal, that's about 0.866. Close enough. The next one's a 0, so we'll call that good enough. Minus 100 equals 0. So we'll add the 100 over. So we have T2. 2 times that number is going to be 1.732-ish equals 100. And then we just divide both sides by this, which is radical 3. So 100 divided by that answer is T2 is 57 point, we'll round to 2 decimal places, 74. This tension, because we did everything in meters and newtons, this is also in newtons. So that's the tension that the little kid has to apply. This is like 40 pounds, 50 pounds of force, maybe. It's not that much. Actually, no, it's like 10 pounds, I think. I'm not 100% sure. The conversion rate is 1 pound is about 4.4 newtons. So divide that by 4.4. Carry the 8. It's like 16 pounds or something like that. So not very hard. But what we're supposed to learn from this is a couple of things. A, we learned that we can do sum of torque equations, and they work exactly the same way as sum of forces equations. But there's a little bit more choice. The positive, negative is not quite as obvious, like up, down, left, right. So in general, counterclockwise is positive, but if you want clockwise to be positive because you're left-handed, go ahead. It doesn't matter. Just be consistent. It equals either 0 or I alpha, which is spinny mass times spinny acceleration, which is very similar to Newton's second law. The other thing we learned is that you can pull with a suboptimal, let me switch colors here. A suboptimal angle, let me switch colors one more time. A suboptimal angle with less force, but because you're pulling with a twice as long lever, you can still pull way less. So having longer levers is very important. And don't let anyone tell you different. Yeah, it's fun. I like torque. Torques are fun. This is a real thing at the Arizona Science Center, I believe. If that's open and COVID's over, go check it out. This thing's tight. But make sure if you're going with a date or something, let them win, regardless of anything. Just let them win to make them feel good about themselves. So when you do it, make sure they get the one where the rope is attached farther from where it pivots. And then it's really hard to lose on this side, honestly. I think I lost to like an 11-year-old last time I went, and it's because that lever is just so much longer that this 11-year-old is pulling at least twice as hard as you are. It literally doubles how hard they're pulling. So little kids beat like grown adults all the time, and it's so funny. So check it out. And there you go. There's your notes. Hopefully we're not leaving anything out, but that's kind of the gist of it. If you have any preguntas on your homework, or you think it's too hard, just let me know. Say, hey, Mr. Barton, you did a real lousy job with that video. I liked and I subscribed because I'm a dedicated supporter of the channel, but I need help with question number 4. Let me know. Otherwise, have a wonderful rest of your day, you guys. I'll catch you guys next time.